Electrical Engineering Technology at Buffalo State College, focusing on the control system sequence, ending with magnetic levitation investigations. The final course is Control Systems 2, last semester senior year. The course before that is Control Systems 1. Course before that is Networks. Course before that is Electrical Engineering Basics 2 and Electrical Engineering Basics 1 before that. And then a math review before that. Calculus 2 and Physics 2 precedes those courses, and Calculus 1 and Physics 1 precedes those. That is the control system sequence. Each course builds on the previous course. This is the Magnetic Levitation Project at Buffalo State College for Electrical Engineering Technology seniors. Magnetic Levitation Control Circuit. This is the electrical control circuit. This is the metal globe that is levitated. The electromagnet makes the magnetic field that lifts the globe. The infrared light-emitting diode shines its light on the base of the infrared transistor. As the globe moves down, the transistor turns on more, which increases the voltage at signal F. The first op-amp is a follower that creates a buffer between signals F and A. The second op-amp is an inverter with gain proportional to its feedback potentiometer. The third op-amp is a practical differentiator with gain proportional to its feedback potentiometer. The second and third op-amps implement a proportional derivative controller. The signal at B is proportional to the voltage at A. The signal at C is proportional to the rate of change of voltage at A. The fourth op-amp is an inverting summing amplifier that adds the voltages of signals B and C, which drives the base of the power transistor, which controls the current in the electromagnet. The diode across the electromagnet protects the fourth op-amp from potentially large voltage spikes if the magnet current stops abruptly. Note carefully the voltage supplies: 5 volts to the sensing circuits, 15 volts to the power transistor, plus 15 and minus 15 volts to each op-amp. In summary, an analog PD controller was described. The proportional gain is adjusted by the proportional potentiometer. The derivative gain is adjusted by the derivative potentiometer. That was the final project in the control system sequence, Control Systems 2. In Control Systems 1, there's a servo motor system. This is the feedback mechanical unit. This is the feedback control unit, control panel, patch panel. The mechanical unit is connected to the control unit through the ribbon cable. The control panel is connected to the computer through the USB cable. System is powered by a power supply, plus and minus 15 volts and 5 volts. there are two shafts. One shaft is the primary shaft, the motor shaft, the one that you see turning. Connected to that shaft through a series of pulleys is a secondary shaft. The gear ratio is 32:1. The digital display shows the output shaft speed in revolutions per minute. To detect speed and position of both shafts, there are a couple of features. The incremental encoder, the black bands that you see rotating, are detected by the pickup sensor here, and the speed is also measured directly with a tachometer. They call it a tacho generator. The position of the output shaft is detected by the gray code. That was the servo motor system used in Control Systems 1. The Networks course provides a theoretical foundation for the control system courses. Given this time domain function equals 13, we really mean a step function of size 13, where the Heaviside function is always assumed in this course, but will not usually be expressed. We want to determine this complex domain function f of s expressed in this form. We really want to know a, b, c, and d. Given the table of Laplace transforms, we know that the Laplace transform of a unit step is 1 over s. A property of the Laplace transform pairs is that a constant k can always be multiplied by both functions. Therefore, k equals 13 in this problem. Multiplying by 13 on the left and 13 on the right, we see the Laplace transform is 13 over s. And equating coefficients, hopefully it's obvious that a equals 0, b equals 13, c equals 1, and d equals 0. That was a theoretical example from the Networks course. Electrical Engineering Basics courses. These two lab courses build a foundation for all other electrical engineering technology courses and give experience with all the usual laboratory equipment. There's the Agilent oscilloscope, the Tektronix oscilloscope, function generator, DC power supplies, multimeters, computer data acquisition systems, and computer programs. Those were the basic electrical engineering courses. Physics 1 and Physics 2, Calculus 1 and Calculus 2, are taught by the Math and Physics departments, and they provide a foundation for all electrical engineering technology courses. Good grades in these courses will benefit you greatly in all the electrical engineering technology courses. We electrical engineering technology faculty want to give you the best preparation possible for your career in electrical engineering. We welcome you to the Electrical Engineering Technology Department.